So today I'm just going to talk about the parallel implementation of pharmacokinetic and pharmacodynamics. Yeah, parallel implementation of this PKPD parameter estimation on Xeon Phi using grid search method. So I'll just first talk about what we are doing as part of TCS. So I am part of the performance engineering research group in TCS Innovation Lab, Mumbai. So we do lots of parallelization and optimization of various applications in life science, CFD, computational finance, and lots of application and even enterprise also. And we have, so I am part of the system group doing lots of optimization. So we are providing lots of services to the customer on enablement of lots of parallel technologies like OpenMP, CUDA, or OpenCL on different hardware based on either is their homegrown product or a standard product. So standard products like OpenFOAM, Amber, ROMs also we have optimized. So I think in the end of the presentation, if I have some time, I'll show the OpenFOAM results also in one dashboard, that what we have achieved till now. So so this work is joint work with the drug development R&D group in TCS. We do lots of this PKPD modeling, which I'm going to touch upon. So this 40-minute session, I'll just break 5 to 10 minutes on the domain part. I'll not bore you guys, and 25 minutes I'll focus on the optimization we have done. So this optimization is on Xeon Phi, and mostly it's a technical presentation on intra-node optimization, that how you can do. The lots of optimization is very obvious, but yes, we should look into that. And this is a very generalized approach that you can apply in any other applications also that you are optimizing. So yeah, let's start with that. So this is the agenda of the talk. So I'll just talk about what pharma industry is facing right now, what are the problems they are facing, and how that PKPD modeling is trying to help them, and what are the challenges while implementing PKPD modeling, what are the computation issues like runtime issues, and how HPC is adding value to that. So that is the agenda of today's talk. So yeah, so this is like the slide. I just wanted to show that how much amount of you could say the amount of money spent to release a drug in the market. It almost takes around 10 years for one drug to come and take $10 billion. So you can see in phase 1, phase 2, phase 3 trials, it can fail anytime. You don't know. So you can see 8.6, you can say it's one of there are 8.6 candidates, but during the phase 3, you can see only few is released to the market, and most of the drugs are failed. So what are the reasons? So if we can identify that failure at the initial stage itself, so we can save lots of money. So that is one of the major challenge in this pharma industry. So what are the solution to that? So if you see, this is released by the FDA, and they talk about that for MDD is the solution that we can think of, model-based drug development. So using model-based drug development, you can actually create, you can define a parameter, you find a parameter which can say the safety profile of any drug, which clearly says that before going to the next step, in very early stages, you can come to know that we should go ahead with this drug or not. So this is one of the major thing that is going on. Not enough attention is being done from the HPC side on this area, but yes, I think in near future, I think this is one of the major areas for optimization. And so model-based development is a part of, like, there are 3 integral parts: integration, innovation, impact. Integration is very obvious that the different data is there, but different formats. So that is one of the challenge, that how you can get the data, the actual patient data, and then how you can use technology innovation to get something out of this, do some statistical analysis, do some PKPD analysis, and then get the faster results of the result. And then this is the impact. So lot more medicine can come. So this picture I just purposely put that what is happening in the phase 1, phase 2, phase 3. So you know that in a preclinical trial, the drug is injected to the mouse or like rat and any animals. Based on this, it can decide that how safe to try the drug on phase 1, which is called first in human. So first in human, actually you try in some tens of people. Phase 2 you try on hundreds of people, and this is like the phase 3, you can say the population PKPD, like you have to take the Australian guy, African guy, Indian guy, lots of, so you do the population PKPD at the last. So each phase is very important. Drug can fail in any phase of time. So PKPD modeling, what at TCS we are doing, we're just trying to understand that whatever parameter, so we take some samples on human. Based on that samples, we do statistical analysis, modeling, and try to get the parameter value as close as it can be to say that, okay, we should go to the phase 2 or not. So this is a, I think, very good diagram of what is PK and PD. So PK say that pharmacokinetics means whenever you take a drug, what your body does to the drug. So, and the PD, Pharmacodynamic, says what drugs does to your body. So this model, what in TCS, and it's a very famous model. So here the research is going on in TCS that if you use this PK-PD, we can say, so in PK you can say the concentration versus time, and codynamics also you can say that what are the values you can get the different phases of time versus the I value. Then finally we have to find the response versus dose. Whatever dose you are taking, what is how the body responds. The 250 mg is fine or 150 mg is fine. Some parameter you need to find. I'll show. So, and different parts, so yeah, I'll show them. So this slide I'll just skip it, but here we are talking about, we are taking the compartment model. There are different approaches we can take. So in TCS we are taking compartment model, which is a well-known and good model in terms of taking. What is compartment, I'll tell you. So you can see this, you inject the drug to the body. Each organs of the body, you can say the compartments. So heart, lungs, liver. So the drug is like distributed in all the compartments, and then you reach the equilibrium state after that. So you can see this is one of the model. The concentration, the formula that you say, and these are the parameters, A, B, C, alpha, beta, gamma, that you need to find. So concentration and with respect to time, and this value you need to take. So you cannot, you can say that, okay, you can just capture this value and run this model. You don't need to do any statistical modeling. But the thing is, this value you cannot take for all time duration. You can take few samples, and based on few samples, you can do PKPD modeling and try to see that in the space, grid space, if you search, which I'm going to explain, how you can get the accurate value. So this talks about that what is this alpha, beta, gamma, ABC, alpha, beta, gamma, like you find the elimination, distribution, and in the body. So you just slide this for the backup, but I'm not covering. And this is the 5-step approach that these two approach with PKPD that we are finding, and we are saying that, okay, this parameter bound selection is very important. What is parameter bound? Like for parameter A, what should be the range? So that is based on the scientist experience and various discussion and various data. But IP estimation, the initial parameter estimation method, you have two approaches, either deterministic or random. So deterministic means you say that, okay, I use grid search algorithm and I just do brute force. I'll just go over all the entire space, try all the permutation and combination and get the final value. The second approach is the random. The random is like based on experience, but this is not accurate. This is very fast, but you'll not get the accurate value of the medicine. Okay? So that's the reason we have chosen the grid search as an algorithm. So yeah, I think I'll just explain quickly what is grid search. So in grid search, you have to first create the grid for this model, for building a model. So this grid, for example, you can say that you have upper bound, lower bound value, and you have the grid points. The more the grid point, the more accurate solution you have. So I'll just explain to the next slide how it looks like. This is an example of two parameter. We have seen the 6 parameter like A, B, C, alpha, beta, gamma. This talks about just the 2 parameter, and you see how your grid search, what is grid points, and based on this we'll do the calculation later, the optimization. So you can see that the number of parameter we selected 2. So whatever number of parameter you have, you can define the dimension of your grid. So in previous case, it was a 6 dimension because you have A, B, C, alpha, beta, gamma, 6 dimensions. Here you have 2 dimensions. This number of grid points decide how many grid points you have in each dimension. So you can see that the number of exploration is n to the power p is 16 here. So 16 grid point, so 16 combination of the value you can have, and it's like this. And you can get the best parameter which is closer to the measured value, and take the call that this drug is safe or not to get into the next step. So this is one of the model example, like we have optimized around 60 to 70 models like this, and we have to run it together. So it's a bit complex, but this is, I'm taking one example only. So this is just SRS value, what I was talking about. You have the observed value. So I'll just show you, this is a real patient value that you got from the different places, different medical institutes and medical colleges. And this is the model that we have. So basically concentration versus time, you have this value. So in this equation here, the SRS value that you have to calculate the minimum value. So for example, in 16 exploration, observed minus predicted, and you have to do square of it and then add it, and you find SRS for each grid point. You think about like for bigger solution. I'll just tell you. Yeah, and the more the grid points you have, the solution will converge here. You can see. For example, in this case, the grid point is 3. So you have more spaces in this particular dimension. But if you have more grid points, your solution will converge, and you can say that, okay, this drug is good or not. Okay? So this is just an example that you have 6 parameters, and we have taken this lower bound and upper bound is given by the input to the model. You can say that when your grid points are 3, you are not converging. But once you have a higher number of grid points, you can converge for some problem. So this gives that, okay, the higher the grid point, the better you have. So this shows the challenges now. Now comes the HPC part, like what HPC is doing. You can see this 6 parameters, and if you increase the number of grid points, you can see the number of exploration, like number of grid points you need to search. Each grid points, this many grid points you need to calculate the SRS, and you have to find the minimum value, which is closer to the real values which is measured, okay? So this is the kind of exponential issue, exploration versus time, and I can show the time also. So here, we are talking about 23, but if one of the model that the scientist, Dr. R. Narayan, he's predicted that 7,000 hours I need to run the model. And this is, you have to run 100 times, 200 times this model. And he said, okay, just scrap the project with the HPC. I don't do it. I'll find something else. Because I don't want to wait for this many hours, or even 10 hours, or even 1 week to understand that this is a failure or the model is failure. We don't know it is a failure. So they said, so that's the reason this was scrapped. So this was the time when we came into the picture, and we discussed that, okay, can we do something about it? Can we do some optimization in this space? Because they said we have 60 to 70 models, and this is one of the model. Can you just try the POC with this, and then we can do other? So we said, okay, let's try what is. So we got the code, and we had the Ivy Bridge machine, and 12 core with hyper-threading 24 cores. So they generally they nowadays in the company, like whenever some programmer joins, he loves Java. The HPC guys love C and C++ and Fortran. So they written in this, because I don't count this. So what we have done, we just did the conversion, and we got 77 seconds. This is compiled with GCC. So not much, but yeah, the challenge was the entire code is serial in this case. So you have to see. So this is like you just have so many points, 0, 0 to 19, 19, you have 20 grid points, okay, and 6 parameters. So you can see 64, I think, yeah, 64 million points. You have to do 64 exploration for just 6 grid points, 6 parameters and 20 grid points. And they just go point by point, calculate the SRS, then again go here, find the minimum, then calculate the value serially. So this algorithm we changed, and we made it parallel. So while doing the parallel, we just do like this. We just use the threads, and after changing algorithm, we made it so that it can run in parallel. So we just distribute the threads. So they said the plan was to try it on Xeon Phi or GPU. So they said, okay, any of the coprocessor is fine, so that we can run many models together and under different coprocessors and get a good values for the models. So this is what we have done. We just simply among all the cores, we divided the grid points, simple, and then we have the barrier, and then we intra threads, everybody's calculating their own SRS, and then finally after barrier you calculate among all threads minimum. So for example, you have 60 threads on, so you can have 60, you just calculate 60 and get the minimum value. So we started with this. This is a very smaller problem I'm telling. This is just 20 to the power 6. I'm talking about, people are talking about 200 to the power 6, 400 to the power 6. Those type of problems, just think the complexity. This is very small thing. So here with the OpenMP implementation, when we increase the threads from 60 to 40, so we started with 11.62, and then we come down to 6.16. So you can see that there is an improvement, but after 120 threads, we are not getting much improvements here. So we just check that what is the issue, and then you can see that the reason is this, like in Xeon Phi, each thread cannot execute instruction in every alternate cycles. It has to wait for a third cycle, and then it can execute. And this is a compute intensive code, so that's the reason you're not getting any much benefits. So we did Vtune profiling and just trying to understand that what is happening. And this I just wanted to show that how we are doing frame analysis. So Vtune has this feature like frame domain frame analysis for OpenMP debugging. So here you can see this part first. This part is red bar is talking about that parallel region that Vtune shows. Okay, this talks about each parallel region that you can break up in Vtune in the hotspot. You can say that with the line number. So before, like wherever your parallel region start, from there to before the start of the barrier is one frame. So you can say one frame. So barrier is one frame. Outside any frame, this is a serial part of the code. So very well you can identify what part of the code is serial, what part of the code is parallel here. Correct? So and this part, the last part is like your barrier part, which we have in our OpenMP code. So we just I just wanted to show here that how we can ensure that there's not much blocking and something is going fine. So from there we start, and here the first thing that we have tried, because we have to get a good number, 6.16 is not a good, even this is not a good number. So we tried all this precision flags that you can try. So we have to ensure that there should not be any problem with the precision and accuracy. So we tried all these flags in different combinations, and we got 42% improvement from the last iteration just by doing this. So basically, I was talking about OpenFOAM, Amber ROMs. So we have the list of lots of compiler flags. So one of the guys dedicated that he knows that which flag should try in which application and can get benefit. Like for example, some application get very good optimization because of NC alias and FNO NC alias flag. You just turn on, you get very good benefits without any problem in the accuracy. So these flags we tried, and we got 42% improvement. Then when we use the Vtune hotspot, we just wanted to find out what are the hotspot. Can we do something about it? Is there any possibility? Because when we go to the internode, we don't look into the intranode optimization. So this is the best tool, I think. We can use other tools also, but just for graphical purpose, I am just showing this tool. So you can see this here, this equation, that alpha, beta, gamma, the concentration equation, it is taking more time. So we wanted to try different exponential function like floating. This is by default double. So we want to try floating, we want to try with base 2. We wanted to try 2f. So there are different variants that you can try. If you are okay with floating and you don't get any problem with the precision or accuracy, you can try that. And you can see what is the improvement that you can get. So this is the original equation, we were getting 3.56. When we tried EXPF, we just change EXP to EXPF, we come down to by 1 second. So this is, I'm talking about very small computation. If you're having a very high computation, you'll get very good. Here you're getting around 27 to 30% improvement. So I think in Black-Scholes or any financial application also, when you try this, you definitely will get a very good benefits. This is 1 second in 3 seconds is very good. So we tried then, we also tried that directly exponential, this is a log, the natural base. When you change this to base 2, you wanted to see, because some of the white papers I have read, and they said the architecture, especially in Intel architecture, if you try the base 2 instead of natural base, you get some benefits. So in this case, from here to here, I'm getting only 40 microsecond difference. But in other application, I got very good improvement. If I just change from EXP to EXP2. But EXP to EXPF is better. So we stick to that. And then from here, when we tried this, EXPF with base 2, the results are almost similar. So we didn't get much benefit. But yes, 1 second we got because of this, so we stick to that. So 20% improvement without compromising on any accuracy. Then we have taken another hotspot. So this is a very small thing that generally we skip, that the Fmax calculation is happening. So we have found that, okay, this is taking some high time. Can we, what is the problem? So we did some analysis, and in the assembly also they are showing some lots of overhead generated by the compiler, because it's a standard function, right? So we thought, okay, this is a very simple function. If we just remove this and apply normal calculation, we have reduced from 2.57 to 211 second. It is 17% improvement here. Then we did again the Vtune analysis, and during the analysis we found that the vectorization intensity is not good. So sometimes tools give me some different output, but yes, so I was not just relying on this vectorization intensity. You can see it's 2.7. So in the Xeon Phi you have 5 and 12 vector bits. So at least you can have, you should have vectorization intensity of 8. So the next way to verify that this is right or wrong, we have used the vectorization reports. So in the vectorization report, it is clearly saying that the loop was not vectorized. So there was some dependency in the loop because the way the algorithm is written, and they are doing some checks later. So we have just checked that, and because of this if condition dependency, the loop was not vectorized. Generally, this is not vectorization friendly. Also, in this function, like when we go, this xf variable is going to and copy to some other variable, so compiler is confused and saying, okay, I will not vectorize, because there is some dependency. Xf is copied to some other variable, and from there you are doing the computation. So we said, okay, can we put this complete function here, or remove this dependency? Second thing, can we remove this and do it in the algorithm beforehand? By doing this, see the improvement. And the first, when we collapse the function, and by doing this, just by removing the if condition. So from 2.11, we have come down to 1.35. And from 1.35, we have come down to 1.28. So now this is the vec report, sorry, which says that the loop is vectorized. And you have no issue. So this type of optimization you can apply in various places, and you can definitely get lots of optimization, very good results. So yeah, so this is one of the other problem that sorry, I got. The div operation always costly. So whenever you go to div operation, in the manual says that it takes 8 cycles or more than 8 cycles. And if you calculate the multiplication or addition, this is only 1 cycle. So there is 8 times overhead is there if you use the div operation. So you have to see in the code. So for example, in one of the example of OpenFOAM where you have Gauss saddle loop and where we have a div operation, I just removed that, I got 20% improvement. I just changed the algorithm. It's not, I need to do lots of changes in the code, but yes, by removing that, I got very good improvement. So this is very, for Xeon Phi, it is tough. We should avoid these things. So by removing this, you can see that we just included the loop. This is the algorithm change. I'll not go over it, but just by doing this, this is come down to 16 seconds from 100 to 16 seconds. And you can see the improvement from 1.28 to 0.68, 46% improvement. So this is again the Vtune analysis. I don't know why, I need to check, but yes, this was showing 0. I need to, I raised a bug in that. So they are finding it out because it says that whenever you have completely vectorization, sometimes it comes as 0. So, but yes, with the vectorization report, I verified. And you can see the runtime also reduced. This is generally some Vtune overhead is there, but you can see that optimized code and over this code. So this is a pragma director, very obvious, but we have tried this because of load balancing. So dynamic load balancing in the OpenMP threads, so that OpenMP threads can get shared dynamically. Whoever is idle get more chunk. So with this, so we did not get much, but I just wanted to include because in other application you may get. So this is a pre and post vector comparison of the analysis that all this hotspot, Fmax, temp, this is almost gone from the list. It's completely gone. So finally, I don't know, my team member is not happy. He's saying we should try something more. And so one of the exploration, the function called stack exploration of Vtune, system level analysis, we found that the malloc is happening. So why it is taking too much time? Because this is not the case with Xeon. Why? Because Xeon does not have that overhead. But in Xeon Phi, this is and even on the GPU, this is a problem. So if you just change the code from dynamic to normal static allocation, you got 35% improvement on Xeon Phi. So you can see in the Vtune, that is gone. The malloc is gone after analysis. So, and then finally the symmetric mode came that because we have the Xeon and Xeon Phi, and we wanted to try both together. So we have the symmetric model. So we have 24 threads here, 60 threads here, and then but catch is this is more powerful code than this. This is 60 and this is 24, but this is much powerful. I think, I don't know, Intel says sometimes that 10x more or 8x more than this. So what we have done, we have divided the number of grid points among the cores in such a way that this get approximately 1.7 times than this guy. And because of that, you come down from 0.39 to 0.22 seconds in the symmetric mode. So it's almost, you can say from the serial version, it is 350x improvement that you got because of these optimizations. So you started with this, and so what I'm saying, I'm trying to bring up here is with the small things and small micro architecture level or code level optimization can give you this benefits. So whatever 350x if I'm getting here, so if I'm running this model for larger number of workload, I got a huge improvement in that. So the scientists are now, the lab is saying, okay, we want to try all these models. So we converted all the models. So it's like with this proof, so other models have different challenges also, but you need to apply all these skills, coding skills. So this is only the 10% of the code that optimization we do, but in other applications we did lots of optimization at the prefetch analysis, Vtune counter level analysis, L1 hit ratio, how we can improve that on Xeon, Xeon Phi, and GPU also. So yeah, that's all from my end. I just wanted to add one more thing that same optimization that we have done in OpenFOAM. This is first time I'm releasing this number. We got this number. I think this has not been published and not being achieved yet on Xeon Phi, this number. This is, I'm talking about motorbike case, but we have tried with car workload and the real customer workload. All this optimization, apart from some other optimization that I have done here, we have changed the decomposition algorithm. We have our own decomposition algorithm. From 213 seconds, this is you can say Xeon. Xeon is your Ivy bridge. From here, you just got 1.41x, but from Xeon Phi native mode, when we started this 4.2 million, from 635, now we are at 194. And in symmetric mode, when we started, it was worse, 518 seconds. Now we are at 135. So yesterday my team called me on Haswell, we are at 1.7x. And on 8-node cluster, we are at 1.4x. So, and if I'm saying 1.4x, this is the optimized 24-core versus symmetric mode. See the calculation here. So optimized, not the baseline or not the 1-core comparison I'm doing. I'm saying 24-core best and then symmetric mode. And the same thing that we have done because of this custom designed decomposition between Xeon and Xeon Phi, the way we are allocating and trying to reduce the MPI. And all this optimization like prefetch. So one of the example is, for example, how the original, when we started, this is a Xeon MPI profiling, Xeon and Xeon Phi. And so you can see the compute part, blue part, is way different. The Xeon is mostly in the compute, Xeon Phi, and Xeon is very early, it just compute and sit idle. And after optimization, you can see the balance. So yeah, I think I'm just ending my talk here, and I'm just open for the question.